Pushpa Giri is our resource person for this session. She's an assistant professor in Department of ECE, NIT Patna, and she did her bachelor's degree from University Institute of Technology, RGPV Bhopal, and her master's degree from Motilal Nehru National Institute of Technology, Allahabad. She did her PhD from MNIT, Allahabad. She has over 8 years of research experience in research and development as well as in academics. She has some high impact publications in reputed journals like IEEE Sensors. Her research interests include microelectronics and VLSI design, fabrication and characterization of thin films and nanostructures, nanoelectronics and photonics. And we are very fortunate to have you in this session, ma'am. I request Dr. Pushpa Giri garu to take over and handle this session, ma'am.
Thank you so much, sir, for a brief introduction. As in the first session itself, I as sir, am I audible?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
And PPT is also visible.
Ma'am, there is a problem with signal, I suppose, ma'am.
Okay.
It's okay, Ramon. It's not okay, ma'am. Yes, ma'am.
Visible?
Yes, yes, ma'am. Visible and audible,
Okay,
ma'am.
Thank you.
Good. Yes, ma'am.
Okay, sir. So in the last session itself, I told you, I described like so many devices and their application in optoelectronics things also. So in the last session also, I told like solar cell these days, solar cells, what is the importance of solar cell, and these days actually each and every researcher wants to work on the solar cell as it is just what you can say like hot cake these days. So each and every researcher wants to work on the solar cell. Why? Because since ages we are not able to actually get that efficiency what actually we want, because till now the maximum it is like we're using very high cost material and very qualitative material, but in the commercial purpose also we are not able to achieve that particular thing. So today actually we are going to talk about the recent trends on the Perovskite tandem solar cell. So already solar cell, each and everybody knows about the solar cell. So what is this Perovskite tandem? What is particular what perovskite and solar? We are going. First we will see. What is how many solar cell actually there exists later is what was the evolution of our solar cell, how it came into the picture. All of the sudden it in pumpers, how and it started from that particular time to 2020, how what is the growth rate and how it has been this particular efficiency we have achieved, and what are the limitations, and what are we are having challenges that we can remove. Then we will go for the tandem solar cell, that is TSC. Tandem is nothing but we are having the multi-junction solar cell. Generally we are using solar cell like single junction, two junctions. So here we are going to use the tandem, that means 3 junction also, 4 junction also, like that only we are going to see. Then we will see what this perovskite means. Okay, so we are going to see the perovskite tandem solar cell also, and then what actually how many types of this perovskite tandem cells are existing, and I mean how many things we can actually incorporate. Like these days graphene is very much I mean famous these days because of the good property like conductivity and definitely the I mean the current, and definitely the efficiency. So because of these reasons graphene is also I mean these days very much potential candidate. After that we can see the quantum dots also, like how the quantum dots also can be fabricated along with the so these are things we're going to discuss today. So just I'm briefing like how, and then finally we'll see the future scope, what are the application of this particular thing, where we can actually we can apply this I mean this PTSC like that. Okay, so these are the things. And why actually this solar cell, we are more focusing on the solar cell because I mean these days our energy consumption, it is continuously increasing, and it represents one of the biggest challenge, actually one of the biggest challenges faced by the human being in the next 50 years, which actually it is going to make exploration of this carbon free energy resources, and that to an urgent task to resolve the fossil energy shortage, and climate changes problem also. So many problems are associated with the I mean the carbon energy, like coal and petrol and all these things are there. So fossil energy are there, so that we don't want. So that's why the solar cell actually it came into the picture, and that to the photovoltaic solar cells. So photovoltaic solar cells are actually one of the key technology for realizing what you can say decarbonized economy and of a sustainable energy supply. That is very much important, that it is having a sustainable energy supply because we our sun is an inexhaustible and a very clean energy source. So to achieve this carbon free power, because we are because if we are using carbon, so definitely I mean it is having a side effect, it is having a pollution in our environment. So we want a total I mean the of energy source which is I mean not which is a I mean pollutant free kind of. So that's why we are going for the solar cell energy. Okay, and we can see like to achieve a carbon free power supply like that. And one more thing is like to achieve this carbon free power supply by, if we can say like by 2050, the installed photovoltaic generation capacity, it has to be increased even more than what you can say like 22 or 23 terawatts. Okay, terawatt. So however the mainstream like photovoltaic manufacturing cost, it I mean have been continued to it is being reduced to extensively over the past decade, and now the cost of module amount to less than half the overall solar photovoltaic installation cost in the utility scale projects. So these are very important things we need to keep in mind. So because of these things only, the increasing the overall this one more thing, whenever we are talking about the solar cell, so some small things I'll tell you, that is which we are going to I mean use generally, like PCE, that is power conversion efficiency. So power conversion efficiency is nothing but overall power output of the module per unit. Okay, so that I mean the increasing the overall power output of module per unit area, that is power conversion efficiency is the surest means to continue to drive down the overall cost of the installed PV generated electricity. So if our efficiency is going to increase, so definitely our cost will be reduced. Okay. And that I already told you, like a tandem solar cell. So tandem solar cell is nothing but tandem solar cell. It is nothing but it is a multi-junction solar cell. Okay, which is the great potential and one that is a benchmark. So it has a potential that it can break, this can break that particular efficiency more than 33-34% for a single junction solar cell with a band gap of like electron volt under the sun illumination, and thus we can this LCOE cost, that is levelized cost of electricity. Okay. And if we will go further, like this is what I talked about the single junction solar cell. So if we will go for the double junction, or if we will go for the triple junction or three junction, you can say like continuously infinite junction, which is ideal case. So in that case, so definitely 100% we can think, but it is not till now achievable and all the things. So in that case, the relative emission and considering both and electroluminescence of other cell in the cell. In particularly the efficiency we can expect if we are having a junction, 4 junctions, so definitely we can expect that efficiency will be where it is going to increase. Okay, so theoretically we can see like this particular slide you can see is like theoretically efficiency of a single solar cell based on the theory we are having. So we can see and we can easily identify like not more than 30%. Like if our it was clearly visible, like whatever type of cell we are going to use, okay, the maximum to maximum is like 30 or 30 to 35% efficiency. So because of this reason only, we are actually switching our moving towards a multi-junction, that is a tandem solar cell. So you can see over here also like gallium arsenide, the most the most costliest material we are having in
There is, excuse me, ma'am. Sorry to disturb. Sorry to disturb, ma'am. There is a problem with the voice, ma'am.
Optoelectronics, and whenever we are going we see that maximum and max. Hello,
Ma'am, there is a problem with the speaker, ma'am. I suppose a voice is breaking at times.
now also it is
Now it is okay, ma'am, but at times it is breaking and it is prolonged. It is just like it is sometimes somewhere lagging, ma'am. That's it. That's the problem.
okay.
It's now clear, ma'am. You proceed.
Now
ma'am.
it is clear.
Yes, ma'am. Yes, ma'am.
Okay, actually I was keeping the earphones, so I'll remove. So
Okay,
it will be better, I think.
Yes, ma'am. Yes, ma'am.
Now okay?
It's okay, ma'am.
Yes. So, I mean, whatever the material we are going to use, like gallium arsenide, or even the perovskite we are going to use, or the silicon base we are going to use, or this, I mean, amorphous silicon. So what are dye based or cadmium tin based we are going to use, or this gallium selenide based if we will use. So whatever the material we are going to use for solar cell, so I mean that will be not effective that much, because the single junction, so it is not as junction 4. So because of that reason only, we actually we went for this. I mean, what you can say, the double junction and all. So I mean till 1990 also, if I'm not wrong, till 1990 we were working on the single junction only. After when actually this space mission and all, I mean, and through actually required the more efficiency, the switches that must be having the more efficiency, lightweight, as well as cost effective, because this time we are going for the commercial purpose. So at that particular time, actually this came to the, so I mean, so because of this, by using the arsenide, we were able to achieve the efficiency greater than 30%. It was about to 22% or something, but it was, you can say, the gallium indium phosphate. So to obtain much higher efficiency, the band gap of this, I mean, gallium indium phosphate and gallium arsenide need to be decreased to extend the absorption region, which actually leads to development of gallium indium phosphate 3 junction tandem solar cell. So all these, actually we wanted, I mean, the absorption region with the, I mean, with greater wavelength. Because of also, actually this, I mean, into the picture. So these were the reason why we came. One, so we can say that our record, I mean, whatever the record in my junction solar cell only, but these days, like 6 junction solar cell also, I mean, the researchers are working, and that too, the 6 junction solar cell, it is actually composed of it is giving like 47.1%. That it is too much compared to, like if we are talking like 4 junction fabricated, because most of this you can easily see, like most of these chemical are generally organic material. It is actually combination of organic and inorganic materials. So typically we are going to fabricate these solar cell via metal organic CVD, like metal organic chemical vapor deposition, or you can say like molecular BPTXC, or we are having the cheapest. Fabrication is not a tough task these days, because I mean NIT Patna is also going to not going to, actually in NIT Patna also we are developing one fabrication lab. So we are having the sol gel technique, and we already got the DC sputtering. So melan and basic fabrication techniques we are also having. Those we fabricate our solar cell, and for the characterization purpose we are having so much of collaboration in like MNIT Allahabad, and like IIT BHU, and IIT IIEST Sipur also we are having. And NIT Patna also we are having, like those. Other than that, we are having some collaboration with the private companies as well, or in some collaboration. So we can fabricate. Only the thing is, like, we need to get that kind of efficiency, because generally we are working and we are not having that much facility what like foreign university and all they are having. But definitely we can achieve also if we will do more and more experiments, and if we will go through more and more studies. So definitely we are also we are having that much vision. So definitely we also can achieve like so definitely it is not that kind of thing, like we cannot achieve those things. So these were the drawbacks of our single junction solar cell. Now we are working for this multiple junction solar cell. Now we will see for this working principle. So how it is actually, working principle of single junction and multiple junction solar cell. So how it is actually working, and what is the basic principle behind this work. So those we will see. So first diagram, you can see like conduction band is there, valence band is there, how this electron and this whole, so valence band downward is the valence band, and the upper one is the the conduction band. So so in the the tandem solar cell are you can see that these are actually we can create. You can say the tandem solar cell. Single junction solar cells are stacked, okay, on one another. Like we have created one single junction solar cell. Like normally, how the solar cell is being made, created. Of the solar cell. So I'll not go deep. So one single junction solar cell we can create over that we will keep the another solar cell. So like step by step we are going to keep, um, typically with the the top one we will keep the wide band gap solar cell absorbing high energy photons, and the bottom one will be a narrow band gap solar cell absorbing the low energy photon. Understood what I told? Is like upper one, okay. So generally we are stacking single junction. We are stacking so that the multiple junction can be created. And how we will stack? We will stack in such a way that the upper one, the topmost one, what you can say, the topmost one, it should be the wide band gap solar absorbing the high energy photon, and the bottom one, it should be the narrow band gap solar cell absorbing the low energy photons. Okay, thus realizing a broader region of the wavelength absorption. Generally, we want this only. That's why we are going for the multi junction, or you can say the multiple junction solar cell, in order to absorb the broader range of the wavelength. Okay, which actually it gives the hot uh, carrier thermalization loss, and which actually reduces the this hotization loss, and by one, so it can actually we get the, okay. So this of this multiple, what you can say, this tandem solar cell, it can be estimated by simple, some formulas are also there, and it will be actually it can be calculated by some formulas which we will discuss later, that efficiency formula, okay, in terms of the flux and all. So right now we'll not go into that. So till now, how this valence band and this particular conduction band is, okay. Uh, so generally, by keeping these things, we are facing sometimes two intrinsic losses as well. That is the losses also we the types of perovskite, what you can say, the tandem solar cell or multiple solar multi-junction solar cells. Okay, so we can see over here, like we are having numerous, we are having like number of perovskite solar cell associated. Initially we were working on the silicon solar cell, then simply perovskite solar cell also it came into the picture.
Madam, please unmute your mic, ma'am. Pushpa, ma'am, please unmute your mic, ma'am.
Yes.
Okay.
Yes. So we are having like silicon solar cell, then perovskite solar cell, organic solar cell, this quantum dot solar cell. So these are the types of perovskite solar cell. Now we'll see. Yes. So, so yes, yes. Yes. So we are having different types of this. We can see over here, like A and B. We are having. Sorry. First, like A and B, we are having 4-terminal configuration. We are existing like 2 configuration tandem solar cell. First one is the mechanically integrated 4-terminal monolithic 2-terminal configuration we are having. So first A and B. Oh, 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 sorry, but this is D and E. So A and B, these are the 4-terminal one. Okay. And this down one, these 2 are the 2-terminal one. Okay, so 4-terminal configuration when we are going for this fabrication of this 2-terminal. So let's clear you what is the 4-terminal configuration. That is configuration, the mechanical stacked and the spectrally split. So you can see that so it's nothing but we are having the mechanically stacked and one is called the spectrally split configuration. Yes, the top coupled. You can see independently trained by others. We can easily see like 2 devices are there, and these 2 devices are connected. So individually, this efficiency we can, we can maximize efficiency individually. So, however, the optical losses are, it can be expected to be this absorptions and reflections from the transmitting transparent conductive oxide. Okay, like TCO is nothing but we are having the transparent conductive oxide. So this, I mean, we can see this particular region satisfied, and the fabrication and this assembly as well. Definitely, single junction we need to create. So one substrate will also like to keep that much of substrate. Therefore, definitely for multiple substrate, we need like the overall cost will also be enhanced. So therefore, this four terminal this TSC have so far I mean from this industrial what you can say from the industrial application, generally we are not seeing four terminal one are actually I mean the two terminal. Okay, so next one is we are having terminal also transparent conductive electrode, like you can see here TEUV, that is a transparent conductive electrode. And one single transparent conductive electrode, and we can add two with multiple T. So here, like but see, little bit different. Okay, so how it is different? Like here we have used the TJRRL, but here we have used the TCO2. I mean, two times we have used the TCO, or you can say the transparent conductive oxide. So because of this region, I mean, it is little bit different, or you can say it is a mechanically stacked two terminal, and first one was the single, I mean TCO. I mean the solar cell having the single TCO, and here it is a mechanically stacked one. Okay, so I mean. In 2T TSC, both optical and electrical coupling are also be required, right? So 2T TSC require fewer power electronic circuits, and that's why it is I mean more attractive respect to installation. Or you can say the photovoltaic system, because the potentially lighter weight and lower cost. Because here you can see we are having the two terminals. So two terminal, that means less substrate only we are going to use. So definitely it will be lighter in the weight, and it will be in the lower cost. Like so, however, the fabricating 2T TSC remains a great challenge because they require a sophisticated optimization also of I mean series of factors like current and lattice mismatching, because here we are using the TCO and double TCO. So I mean the lattice mismatching, I mean in the last session also I told you what is the lattice mismatching. So lattice matching is also required, current is also required, processing compatibility between the subcell, these are also required, appropriate recombination layer, and this tunneling junction. So here this TJ and RL is nothing but we are having the recombination layer and tunneling junction. So these are the things by which it is, I mean, a little bit difficult to achieve, but it's not like it cannot be achievable. So in the industries and all, can say like because of the lighter weight and cost effective, we are using two terminal one. Okay, so these are the things like in terminal wise we can see. Next one is the Perovskite tandem solar cell. Since starting we are talking about the Perovskite. So now we'll see what is this actually. This perovskite means what is this actually is. So we already spoke about how many types of perovskite solar cell are actually existing, and what you can say, how it can be achieved, and what the configuration, like 2-terminal, 4-terminal, each and everything we have discussed. But what is this perovskite that we didn't discuss? So now we'll discuss about this perovskite tandem solar cell. So how it, what is this actually, and how it can be achieved, where it can be used. So first we will start with the crystal structure, then we'll see the band gap of this perovskite solar cell, band gap of this solar cell, then we'll go for this, how it can be achieved, how it can be fabricated. Then we'll see the different perovskite solar cell structure, like NIP mesoscopy, NIP planar, PIN mesoscopy, PIN planar, then nanoparticle and all those things. So these are the things we will discuss in this particular slide. So perovskite tandem solar cell is nothing but it is actually a metal halide. Okay, metal halide perovskites with the formula of ABX3. So in the first one you can see like ABX3. So A is cation, B is anion, and then X, it is the anion. Okay. So A plus, B2 plus, X minus. So that is going to make a formula of ABX3. Okay. So it was, if we'll see little bit history, then it was first reported by Weber in 1978 itself, this perovskite tandem solar cell. But later we have researched and we worked after this 90s only. So in the ABX3, A plus is the monovalent cation that you can see, like A plus single. It is, so that's why it is called the monovalent, and typically we are using the methyl ammonium, that is Ma plus. Okay, methyl ammonium, and that is nothing but CH3NH3 plus, and or you can use the form MEDNium, like Fa A plus, that is HCNH2 2 plus, or we can use CS plus, or we can use the rubidium, or their mixture. So these kind of material we are going to use for this monovalent cation, or you can say the first formula, that is A. Okay, and then we are actually we are going for this B plus. When we are going to use, then this is a divalent cation. So divalent cation is typically metals such as lead, tin, germanium, or their mixture. And this finally the X minus is a monovalent anion, and it is typically halide, like iodine, or boron, or some chloride, or their mixture kind of. And the B, you can see B metallic cation and X anion, it can form like BX4 minus octahedral also. In the diagram itself you can see, and A cation occupy this. When you will see the crystal structure, just go through this crystal structure. So how these these are actually making. Okay, so red one you can see, that is anion. Okay, that is only at the outside of the lattice structure, right? And this what you can say, this B metal cation and X anion, actually BX6 these are making. So this light one you can see that is a B2 plus that is in the center, and these X what I am telling like BX6 it is making. So the 6 anion it is actually surrounded by sorry this B cation surrounded by the 6 anion you can see over here. Okay. So from here, I think you people are extremely clear that BX6, this is in the center one, it is making the octahedra, and A cation occupy the 12-fold coordinate, which is also, it is clearly visible like hole within the cavity. So red one is the A plus anion, which is, just outside the box, and these are making the octahedra. Okay, so the thermodynamically stable structure for different perovskite is actually dependent upon the combination, what combination or what composition we are actually going to use. So here we can see, so for example here we are actually using the MAPB-I3. MAPB-I3 is nothing but methyl ammonium lead iodide. Okay, so that is nothing but MAPB-I3, that is a stabilized as a tetragonal structure. Okay, while if other we will see, then we'll having the cubic structure or some other structure according to the combination at the ambient temperature. Okay, so this is actually a little what you can say, it's earlier we were using the silicon normal silicon solar cell, so it was having it was having a simpler structure, but it was not having that much efficiency. That's why we went for this perovskite tandem solar cell. So definitely the structure is little bit complicated, we can say, and more organic things we are actually going to use, but definitely efficiency wise it is giving actually more efficiency. Or you can say these metal halide perovskites, these are good light absorbers for both top and bottom cell in the tandem solar cell, because of their tunable band gap in the region of like 1.172, like 3.4 to 3.5 electron volts. So for the lower band structure, if we are for the lower band gap material, if you will see, so this metal halide, this TSC, these are the best perovskite TSC. These are the best thing because of this tunable band gaps. And this TSC actually perovskite solar cell, these are normally applied as a top cell, because the typically band gap of highly efficient this perovskite solar cell are 1. This what I told you, that is lower band gap, so 1.6 electron volt, and that is ideal band gap, close to ideal one, that is a 1.67 to 1.75, so which is going to give a long-term energy output and all. So till now anybody is having any doubt, or just I am going through? So any research gap or anything you people are getting, like how the things that can be created, how the solar cell will be fabricated, or just now, just like that it is going on?
So it's going very well, ma'am. We are able to get information. We're getting some information, relevant information and useful information.
Okay, okay. Just now I'm telling you, what are the research gap and not research gap exactly. What is the recent trends going on? Like solar cell, people are making solar cell, so many cell people are making. Okay. But perovskite solar cell, it is into the market these days, and different types of solar cell also, perovskite solar cell. So that also I am going to discuss.
Okay, ma'am.
Okay.
Okay. No, I thought, I mean, it is going little more theoretically, and also that's why people are getting bored.
Yes, ma'am.
So that's why sometimes need to ask whether you people are understanding or not.
Yes, yes, yes. It's good, ma'am. Yes, we can go ahead, ma'am. We can go ahead.
Okay, okay.
Okay, madam. Fine, madam.
No, audience is very nice, very silent.
No, madam. It's fine.
Yes. Yes. So, this is in the tandem solar cell. This actually generally this perovskite solar cell we are applied as a top cell because the typical band gap for highly efficient perovskite solar cell are generally 1.6 electron volt the band gap they are having, and which is close to our ideal band gap region like 1.67 to 1.75 electron volt for this top cell when considering the long term output. So recently, due to the stability improvement and this efficiency enhancement to low band gap perovskite, it is also possible to employ low band gap PSC, like low band gap perovskite solar cell as the bottom cell in all the perovskite TSC. Like silicon we are having band gap is like 1.1 electron volt, or CIGS we are having like gallium selenide, we are having what you can say like 1.08 to 1.15 electron volt. These are the most favorable absorber material for bottom cell owing to their optimal band gaps. So beside the combination of this perovskite solar cell with the third generation photovoltaic, for example, we are having like dye sensitized solar cell, organic photovoltaic like OPV, quantum dot solar cell, like QDSC, have also attracted certain attention due to their improvement in the efficiency, and you can say the low cost, because these are organic materials. So definitely these are from the cost point of view, if we'll see, so it will be very cheap, or you can say very less cost. These must be having like dye sensitized and organic photovoltaic and quantum dots. So efficiency is also high, cost is also effective, roll to roll production will be there, like more it can be generated, and the most important thing, the processing compatibility with the perovskite solar cell. So that's why these, already we have discussed the type of this perovskite. So, like in the previous slide, you can see. So here, why this quantum dot, dye sensitized, organic, or silicon solar cell, or CIGS, or CZTS, these came into the picture because of this region only. Like it is having an organic thing, like the processing compatibility we are having much with the perovskite solar cell. Low cost is there, and that to efficiency is also, it is actually increasing. So, and most important, the tunable band gaps. That is the another advantage of this perovskite TSC, and their high structure tolerance is also there. So that's why these are the good things, and it can be compatibility. It is compatible with the PSCs generally. So next one will see these things like, I mean, so band gap is also done. Next one. Yes. Yes. Next one is one more advantages. One more advantage of our this perovskite for tandem solar cell is associated with their compatibility with the solution and vacuum fabrication. So, I mean, till now what we have seen, like we are having two types of fabrication technique. First is first one is like a chemical vapor deposition we are having, and second one we are having the physical vapor deposition. So this particular thing, it is actually compatible with the both the fabrication technique, but generally we are dealing with the chemical one, MOCVD. But here this is actually the sol by with the help of sol gel process we can fabricate. So here it is actually compatible with the both the solution and the vacuum fabrication method. So this perovskite solar cell with high efficiency are easily fabricated with the low temperature solution method than the high temperature method, because organic material we are going to use. So organic material may lose their property at higher temperature. Okay. So if we are working with the low temperature or with the low temperature solution, so it is going to work like anything. But if we are going for the higher temperature, it will lose their property as well as the fabrication, whatever the efficiency we desire for, it will not be achievable. So then the this, okay. So from the that too from the stability point of view also, like it will not be stable if we will fabricate in the higher temperature. So this is a key issue, you can say, to obtain high efficiency, especially in case of this two terminal TSC. Okay. So like here you can say from this D to G, we are having like a different structure we are having, like NIP mesoscopy structure. That I mean we are having the efficiency of this particular thing nearby 25%, and then we are having like NIP planar structure, so like nearby this 23 percentage we are having the efficiency, and then we are having the PI and mesoscopy structure, so this is also nearby 20%, and then pin PI and planar structure, so it is also having the highest efficiency in between like 22 to 21 kind of this so high efficiency of this perovskite with a different device structure make it feasible to obtain multi junction solar cell by combining with the other type of solar cell having different device structure. So therefore we can say this perovskite multiple junction solar cell, they have become especially attractive both in academic as well as in the industrial field due to rapid efficiency, or you can say the power conversion efficiency enhancement of perovskite solar cell, from initially like it can be initial from 3.8% to 25.2% only in some decade, with a very low production cost, we can say. So, and the two, it is a compatibility with the solution and vacuum fabrication method. And you can say high defect tolerance also it is having, both from the structural and electrical aspect, and tunable bandgap. So these are the advantages like anything. So these are I mean in the earlier conventional solar cell, these were not the things like defect tolerance and both in the terms of structural and electrical aspect, these we were not having. And that too, the most important thing, that is a tunable band gap with TSC. That is if we are going to use the multiple junctions, so that is we can actually tune the band gaps. We can actually, band gap can be tunable. So here these are the benefits and these are the advantages we are having with the perovskite solar cell. So this TSC have a great potential also to enhance the efficiency and reduce the cost of the photovoltaic, while still benefiting from well-established fabrication technologies and the efficiency enhancement strategies of this solar cell. So these are the, see, so many advantages are all there, so many advantages associated with this perovskite. So as a matter of fact, we can say the highest efficiency of this perovskite solar cell, multiple junction and single junction solar cell, significant process, it has been achieved in the perovskite solar cell since the first. It has been like 4 terminal with this, with a less efficiency, but day by day by approaching and by incorporating other material, it has the random development happened due to above mentioned outstanding properties of perovskites and devices. And it is actually it is very good to work on these kind of devices, we can say. So next one we will see, the semi-transparent, now we have seen how many types of this perovskites are there. Now we'll go for this, the most important these days. The people are dying to work on the graphene and this transparent conductive oxide and this nanowires. So earlier, this metal we were using, these days these are the 3 things we are actually replacement in the perovskite solar cell. So that we'll discuss how it will be done. So first we will discuss with this TCO, that is transparent conductive oxide, you can say, a transconductive oxide, you can say transconductive electrode also, you can say, if a metal will be used. So these in this perovskite okay. So now we'll see the semi-transparent perovskite solar cells. So we are having like 3 types of like normally in the normally perovskite cell we were actually doing for this what you can say for anode and cathode, we were using the metals, okay, for electrodes. But now these days this TCO, protective layer, graphene and this nanowire, actually it has replaced the metallic electrode. So why it has replaced, and what is, what are the advantages of replacing? Because without any advantages we are not at all we are interested to change anything, right? So in the perovskite, this tandem solar cell, the foremost issue was to obtain the top perovskite solar cell with the excellent photovoltaic performance and concurrently outstanding the transparency to allow as many as photon in the long wavelength region, region as possible to reach the bottom cell. Understood? So earlier we had a problem that it should be like the photon in the long wavelength region, it should reach to the bottom cell. So that kind of electrode we wanted. So to achieve this goal, the conventional opaque metal electrode in the PSC like gold or silver, it was being replaced with a transparent electrode. Okay, because earlier most of the photons or most of the photons for this long wavelength region, it was not able to reach to the bottom cell. But by using this transparent conductive oxide electrode, all the photon, it was able to reach to. That's why it has been, earlier we were using the gold or silver or any other material accordingly, but it was being replaced by transparent electrode. And as a replacement, the ideal transparent electrode, it should not only meet the requirement of high transparency and conductivity to minimize optical and ohmic losses, but also we are having like 4 to 5 points so that these are the things which we actually needed. Not only the transparency is the only keyword and conductivity, but the suitable band alignment also with the adjacent layer to maximize the carrier transport and collection, right? And second thing was the material and processing compatibility with the other layer of this PSC, because we are having like multiple junction PSC we are having, so multiple layers will be there, so that processing compatibility also it should be there. Next one is we can say the stability also we should have to resist the migration of this highly mobile ions from this perovskite and this layer also. So these are the things we should have to keep in our mind. Then we are having low cost also, that is the most important thing. Low diffusion coefficient, material failure or device degradation. So these are the things we should have to keep in mind. I mean, definitely it minimum points also, like suitable band alignment. Then we should have like you, you can say like uh, the processing compatibility should be having low diffusion coefficient. It should be the most important thing. It should be low. It is there, and what you can say, some different transparent materials. So aluminum doped zinc oxide, or boron doped zinc oxide, or zinc oxide doped with indium oxide. So these are very these are the material which can be used fulfilling these criteria. So it can be also be used in place of this metal electrode. So in addition, the transparent metal electrode like gold and silver nanowires also attractive. This nanowire we have seen. So these nanowires are also the I mean, these are also the candidate because of the, I mean, the protective layer also, it is there in I mean, downside the TCU. So after that, I mean, the graphene is there. So that also we will discuss the graphene and nanowire things. It can, I mean, it can replace the metal thing. Here is the metal and a nanostructured metal electrode like silver nanowire or copper or gold nanowire are also like good choice for this I mean semiconductor PSA because of the removal of this protective layer and the trade-off between the transparency and the sheet resistance approaching that of the sputtered ITO. Like we can use the ITO also. So also applied in the fabrication kind of things I'm telling you. So these are the, I mean, important material also we can use. On semiconductor, semi-transparent this perovskite solar cell is to replace the opaque metal electrode with the dielectric metal nanowire dielectric also deposited via thermal evaporation. I mean, it is just the thickness control also we can do, and it will be like we can reproduce more and more number of times. So actually, use this thermal evaporation method. So with the help of that also it can be, and the adhesion of the metal on the CTL and changes this the growth mode of this metal to layer growth mode. So these are the things which can be it can be done. So dielectric metal dielectric layer, it is, I mean, but they're having some short or you can say high absorption and reflection losses are also related to the dielectric metal. It will be transparent PS. Next one, we are having the most important thing, graphene transparent electrodes. So graphene everywhere, graphene these days, from antenna to electronics to optoelectronics to what not. I mean, which field is not there where these graphenes are not being used. So compared with the TCO, graphene show many advantages. That's why we are actually we are more focused with the graphene. Or not we only, like whole world is more focused on the graphene. So in the last session also I showed a few papers where the in the antenna this graphene based graphene based absorber were made. So I mean in the antenna also it is being used. So it is actually showing many advantages in terms of mechanical, chemical robustness, flexibility, and excellent electrical behavior, such as it is having the resistivity like 100 ohm per square, and high mobility, electron mobility like nearby 10,000 centimeters square per volt second, and classical optical properties, low FCA, free of protective layer, and potentially the low cost and whatnot. So these are the, advantages, like, not one, not two, not three. It is like and so that's why the whole world is behind this graphene. So these excellent features, it actually enables graphene as a potential candidate in the semi-transparent this solar cell. So graphene actually material, when we are going for the fabrication, it is little bit difficult to fabricate this graphene with because graphene we are actually we need to fabricate with the help of this chemical vapor deposition as a TCE top of this what you can say on the top of the solar cell, and which is a big process for the semi transparent PSC and the graphene application in this perovskite and multi-junction solar cell. So generally P dot PSS traditionally uses to enhance the adhesion of the graphene to to lower the shearing by field effect doping. And so these are the things like by which graphene can carrier mobility and decent conductivity, high quality graphene prepared by this preparation technology or transfer technology yet to be developed before its wide application as TC in the perovskite. Because that only I told you, like fabrication of this graphene, it is little bit difficult transferring. So we have to work hard on this particular field. In addition, and that only like nearly been successfully fabricated with high quality scale, although but its application in the large scale solar cell product in tandem. So no doubt that graphene is very nice, very good, but the fabrication is because in the low temperature solution we are fabricating, so it is little. Next, we will see the types of perovskite solar cell. So Next one we are having is the perovskite solar cells. So types of solar cell will describe like how many types of are there and what are the based perovskite. Perovskite living. So this is nothing but four terminated suitable band gap and decent efficiency. It is, I mean, we can say like it is ready to combine them with the bottom cell having the suitable band gaps, right? So in this, I mean, this fascinating new research field like silicon solar cell are undoubtable the favorite candidates earlier. So silicon I mean, module not only have a large market share, more than 90% photovoltaic market, but also the ideal band gap like 1.1 electron volt for bottom cell, as well as excellent stabilities also we are having with the silicon solar cell and relatively low cost at the module level. So, I mean, in the lab scale, got 27% approaching to this. I mean, ideal behavior. I mean, we are having the great challenge to further improve the efficiency in a single junction architecture, and we can say considering the technology cost and say the market. I mean, this the solar cell without extensive manufacturing cost increase. As a result, tremendous progress has been made in the recent years, which we can say like which may most direct approach for the and we can say it is the fastest routes also to realize this efficiency improvement of the commercially available silicon module. So the highest efficiency for this highest efficiency for this perovskite silicon solar increase was 13% and when we reached to this 2020, so it has been increased up to 29-30%. So exceeding the record of this efficiency for this silicon, like normally 25 to 26%, and this perovskite was individually it was having like 25%. Like both were having nearby 25-26%. But when we actually combined these both the things like perovskite on the top and silicon on the bottom, so what happened? Our efficiency it has been increased up to 29.1%. So notable this efficiency enhancement and benefits from the perovskite band gap embodiments with the band gap of 1.55 electron volt. So these are the things like compositional engineering to enhance the stability and management and this modification So these are the things which actually it enhances the efficiency. Okay. So now we will see the schematic of this four terminal this perovskite solar cell. So we can use the filters without filters. So coupled without electrical connection. Thus the shall work at their maximum power output. Therefore, no current or voltage matching is needed efficiency independently. So, and these are the things. Okay. Next one. We are having and one more thing is like to obtain like high efficiency of this perovskite, it also necessary to optimize this silicon cell. Next one we are having like two terminal. Here we are having the two terminal like two silicon and this upper one is the perovskite. So you can say like mechanically stacked 2T 2T. So I mean generally in this one this perovskite solar cell on the this textured silicon bottom cell, more flexibility for the structure design, and we are more focused to achieve the low cost and high efficiency. So generally, I mean, till now it has been researchers worked Thailand only. The 5-3, then deposit is electrically conduct. So you can see over here the diagram. So the transparent adhesive is consisted of we can like only we can get the things and can achieve that particular efficiency. So the efficiency of limb cell percent and the energy band alignment rather than the absorber, it has been proved to be the crucial factor of the influence the voltage loss in the tandem cell. So after that we are having like triple junction perovskite cell also. I mean triple junction, two junction we are having like come to two junction perovskite solar cell, three junction cell composed of two PSC and a silicon solar cell. So like whenever one junction it is being increased, having example if we have one junction and one silicon solar cell, and if we are having three junctions, so we are having two junction perovskite and one junction will be silicon solar cell. Likewise, we actually are increasing junction will be like. So like that only we can increase the efficiency although we are high efficiency, like 29% has been estimated and has been obtained with the help of this perovskite and silicon solar cell. Further research into this estimation of this practical efficiency limit for such a hybrid tandem still unknown. Which type of this PSC architecture like NIP or PIN, it can lead to higher tandem efficiency. So up to now, the highest tandem efficiency reported in the literature, it has been realized using this solar cell, while majority of the past record efficiency for single junction solar cell have consistently achieved like NIP structure. So like contradiction and debates, it is still is like which AGS copper in selenide solar cell. This is also, it has been included like solar cell along with this. So besides the silicon solar cell, other suitable candidate also we are having for making this bottom cell in the hybrid which is having the optimal band gap nearby this 1.08 to 1.15 for you can say like similar to this perovskite, band gaps of CIGS is also tunable in the range of 1 to 1.7 electron volt by varying the gallium and gallium indium ratio. So if we will actually the doping level will be doping ratios, if it will vary, so we are actually able to tune the things. We are able to tune the band gap also. So band gap tunability for both the CIGS and perovskite, it provides the high capability to achieve you can say to a potential higher efficiency. Perovskite silicon and more the silicon solar cell have shared 90% photovoltaic market. These unique advantages include direct band gap, high absorption coefficient, for example 10⁵ centimeter square, and low material uses, high stability, low cost. So that is the most important thing. The cost of the CIGS cell is expected to be like very cheap. It can be like 0.34 in the US dollar we can say, and when we will see in the rupee one, so it will be like 21 rupees or something. Of one solar cell and the two with the efficient percent. So in this technology that are and these are actually very easy to fabricate uh, into the flexible devices which have potential application in building integrated photovoltaic and mobile devices. In addition, both CIS and site are actually able to will several orders higher than the silicon. Then ideal, and it is ideal candidate in the high altitude and space application. Therefore, this undoubtedly this perovskite, the combination of this perovskite and the CIGS, it is undoubtable. It is a very it is actually arising the great research interest because of these high quality and the high quality solar cell, as well as the application in this high altitude and the space things. Okay. So, and similar to this perovskite silicon solar cell, there are two configuration here also, like 40 and 2D. 2D. Actually, we will not go because of the time constraint. Will not go. You can go through all these things like 4-terminal and 2-terminal if you are really interested to read and to work on the topic. Terminal are there. And having the configuration, only inverted structure of this was applied as the top and due to favorable PIN structure. So this was two types are there, like 4-terminal and 2-terminal. Okay. Next one we are having is next one we are having like everything it is being so this one is actually zinc. It has been incorporated in between. So actually both are almost similar. Only the thing is the material composition. So here we are introducing the zinc also in between. So this is nothing but copper, sulfate, and selenium. These are the 4 items. It has been incorporated into this. So this is actually compared with this CIGS solar cell. This SCZT SSC cell, they are also like have advantage of low cost due to the uses of earth abundant, obviously, because cheap raw material like copper, zinc, sulfide, and rather than indium and gallium, here we are not having indium gallium, we are having the copper, zinc, Sn and S like sulfate. Sulfur. So the less cost. So the material cost is actually we can say like one roughly if we will estimate. So it will be like 1/5 of this. Additionally, it is having a higher absorption coefficient of more than 10 raised to multiple wavelength. Understood? In the range of, you can say, like 300. It is having more absorption coefficient. That means it is going to absorb more and more light, and definitely it is having a high efficiency like 28-29%. So it is also a great potential application as a bottom cell in the solar cell due to high band gap tunability in the range of 1 to 1.5 electron volt. And easy selenium ratio from 0 to 1 selenium to by adjusting the chemical composition or elemental composition of these things, it can be tuned, the band gap, it can be tuned very easily. So I mean, more importantly, we can say this solar cell and this PSC are actually well matched both in the terms of optoelectronic property as well as the processing compatibility also via the solution method. We can say for the integration into this monolithic architecture. And compared to, you can say, like perovskite with the silicon or perovskite with the CIGS, all the like PTSCs, perovskite CZTS, it lowest normalization, environmental impact. Like it will be like I mean more environmental friendly. So because it is having the highest efficiency and it is more environmental friendly, so it is being more in the like high performance things, so it will be useful. So next we will see the all PTSC, like I mean compared with the perovskite silicon, perovskite CIGS, TSC, all perovskite solar cell are to their high efficiency via low temperature solution processing tandem solar cells. So this particular it is having the more efficiency than the other one. So this is the biggest advance compared with the other the vacuum deposition method. Okay, but here we can use the low temperature solution processing method also we can use and achieve the high efficiency. So left one I mean the schematic diagram, schematic structure, and the right one is the we can see the same image of this particular. So I mean it is having a great advantage for simple temperature resolution processing. So able band gap and open voltage voltage gain are lower and compatible. All PTs are expected to be a ultimate goal because because they show all the advantages inherent to the thin film photovoltaic, such as easy fabrication, high throughput, use of the flexible substrate for speed. So these limitations are also there. Narrow band gap and with the maximum efficiency is also like this. And you can say with high solvent also. These are the things we can say, like our all PTSC. These are, I mean, this particular solar cell, it is, we are having a I mean, we can so from this we can get more and more efficiency. So in this also we are having like 4-terminal and 2-terminal devices. So next one, so we can use the flexible substrate also, what I already told you. Next one, we are having like organic organic photovoltaic, or you can say the perovskite quantum dots, dye-sensitized solar cell, and other we'll see here only. In the quantum dots, then we are having dye-sensitized, then we are having this cadmium tin. So these are the four, I mean, this is, and that is all are the organic material. So organic photovoltaic, it is also, it can also be fabricated easily with the help of drawing method itself, and then some unique advantages like easy, it can also be easily tunable band, having good absorption coefficient, processing, non-toxicity, and low weight. So these are the benefit of whenever we are going to use the organic photovoltaic. So these are the benefit of using this. So but this is also we can so then in the we can achieve. Next one, we are having the quantum dots. This quantum dots is also like the lead chalcogenide structure kind of things, like PBX, where I mean the lead on X, the combination of, and X is nothing but sulfur or selenide at tin. These are the material for this quantum dots. So it is also a very highly tunable band gaps ranging. It is from 0.4 to 2 electron volt even, only via the size modification and general exciton generation, or we can it is actually indicating the great unique advantage. So for instead, I mean, for instance, we can say like dots. It cover a wide spectral region from 825 to 1750 nanometer, which cannot be realized by silicon or CIGS or narrowband gap. So, for example, all the PTSC with a high efficiency only utilize the photon with the wavelength shorter than 1000 nanometers. So here, if we are going to use the quantum dots solar cell, so we can see like the wavelength, the wavelength it has been increased like anything like 1700 nanometer we have actually we reached. And dots. I mean, in case of those things like graphene is there, so we can use the quantum dot also. So quantum dot, by how we can use light need. So at that particular point, this quantum dot solar cell also we can use. So topmost layer will be definitely the perovskite, and the down one we can use the quantum dot. And the sensitivity, you can say the stability is little bit a problem in our quantum dot. I mean, we have to actually strongly absorb the UV photon with the energy larger than the band gap of this quantum dot. Slide some dots and are anticipated to act as a UV filter for the you can say this perovskite bottom cell. So firstly, prove that if ITO, zinc oxide, nanoparticle and lead, I mean this quantum dot solar cell, it will be used, so it will be excellent stability exposure due to the the use of this PBX quantum dot solar cell, and eliminate the loss also. So it will be very much used if we will use this kind of this kind of thing in this quantum dot. Next one, we are having dye-sensitized solar cell. So dye-sensitized, actually it is these are composed of anode electrode, photosensitizers, electrolyte, counter electrodes. So although the efficiency of this dye-sensitized solar cell, it is relatively low. And they have outstanding properties of low cost. Inorganic semiconductor photovoltaic. Inorganic semiconductor technologies, the energy input needed will this particular thing. You can say, in the weak or weak light illumination, or when this rainy season or that kind of season will be there, so it can actually contribute a good performance. So, and that too, the performance of this dye-sensitized, it is actually dependent upon the dye molecules used in the photosensitizer due to the photo excitation of this dyes. So various photosensitizer also we can use, like including we are having organometallic compounds or organic molecules, or you can say the nature dyes. So these are the things by which we can make this DSC perovskite, and it can be, we can achieve this particular thing. So many methods are also there to enhance the property and enhance the absorption thing, and enhance the efficiency also. So now the thing is, like, we have we have seen like so many perovskite tandem solar cells. So we'll see the which one is the best, right? The perovskite tandem solar cell, it show a great potential in the market, in the photovoltaic market. So if we will summarize, so we'll see, which one is the best. So among all the mentioned, like perovskite TSC, perovskite silicon, perovskite CIGS, all PTSC are among the most promising ones due to their high efficiency, fabrication methods, easy fabrication on the flexible and light substrates. You can say like high throughput, low cost. So it's very difficult to say like which one is the best. So at the current stage, the most promising candidate is, you can say, like perovskite silicon, which represents like a direct entry pathway for the commercialize these. In these days, commercialization, if we will talk, so perovskite silicon is in the most commercial way, and but little, some shortcomings are also there, such as difficulties in the band gap modification and fabricating the flexible devices, indicating like for example, perovskite CIGS is there, so that easily the band gap can be tunable, fabrication is easy, but with the silicon it is not possible. But in the market these days silicon is in the 90%. So this is in the debate only, like which one is uh, what you can say, how which one is the best. So according to the application also, according to the requirement also, we can go through like which one, which devices we need, which device. Like for example, for the space and all purpose, we need, we don't need CIGS, we need CZT, right? So according to that, according to the application only, we need to change, we need to see which one is our thing. So this is the measurement, like how this, this measurement can be done. So this measurement, accurate measurements of this, this perovskite is actually the central to determine the device efficiency, losses, material property. So these are the critical to further efficiency enhancement of this cell. So we can say, like compared to the single junction solar cell, the measurement of this IV and efficiency are more complex and challenging in the this multiple junction solar cell. For large scale, if you will say the perovskite tandem solar cell, high efficiency is indispensable for their commercialization, and low cost and less environmental effect. So by this diagram we can see like how the this IV characterization can be done, how this voltage efficiency will be calculated, like I photon upon Q eta flux. So those formulas and everything will not discuss. So these are the things which can be then LBIC, that is a light beam induced current we are having, that also we need to calculate. And what other than this IV and this efficiency and IBIC measurement, other characterization like UV characterization or photoluminescence or XRD are also useful method to study the properties related material and working mechanism of this, you can say, the tandem solar cell. So with that only we can get through all those things. So with this I would this time is there. Yes, we'll try to finish it out. So these are the some applications in so many places it can be used. And this is what my contact details are. Like, if you are having any query or something, so you can directly contact me with this only. And we have, if you want to fabricate your device, we are having collaboration with the NIT Allahabad, IIT BHU also, as TCPur also we are having collaboration, and NIT Patna itself we are working on this particular field. Like we are constructing, we are making the fabrication lab. Already we are having the software lab, VLSI design lab we are having, but fabrication lab also we are working on this. So if you people are interested for the fabrication and other thing, so we can we can work together in the future. So like, thank you so much for inviting me, and thank you so much for calling me for this lecture, and hopefully you will you have been able to get all those things what I delivered, and in the future we'll work hopefully together. So thank you so much. Sir,
Any queries from audience?
Last time I forgot to share the PPT. Today I'll do so.
Okay, ma'am. Okay, ma'am. Sure.
Vasu Babu sir, I'll share with the Vasu Babu sir. So
Sure, ma'am.
Sure. Yes. So any doubt or any query you people are having related to fabrication or solar cell or anything?
Participants, you may raise your doubts or questions. Seems that they don't have any doubts related to answer.
Yes.
Anyway, thank you very much, ma'am, for this wonderful session on Perovskite multi-junction solar cells, as well as some other applications related to tandem cells and all. This is very much essential for people who are working on wireless sensor networks and IoT applications, where energy harvesting is one of the important parameter, and these kind of unconventional energy sources are really going to be useful for people who are working in emerging domains also, ma'am. We are very much thankful to you, ma'am, for your wonderful lectures, and we have gained a lot from your presentations. Hopefully, we'll be seeing you in our upcoming programs also, ma'am. We are very much fortunate to have you on our team, ma'am. Thank you very much, ma'am.
Thank you so much for inviting me and giving me the platform for this to deliver the lecture. I'm very much grateful. Thank you.
Thank you, ma'am. Thank you, ma'am. Thank you very much, ma'am.
Sir, may I leave, sir?
Yes, sir. Yes, ma'am. Thank you very much, ma'am. Thank you.
Thank you, sir.
Ravi, sir.